Imagine lighting a single candle in complete darkness. That tiny flame produces light that spreads outward in every direction, forming an expanding bubble of light around you. As time passes, this bubble grows larger and larger, a three-dimensional sphere of light surrounding you completely. If you were standing inside that bubble, it's impossible to step outside of it because the light is spreading at the speed of light itself. To escape it, you'd have to move faster than light, something no object in the universe can do. Now, let's visualize this same event in 2 dimensions. That expanding bubble becomes a growing circle around you. If we plot this on a diagram, moment by moment, we get a cone shape extending from the past into the future. This is what physicists call the light cone. It represents how light, and therefore information, travels through space and time. Every second that passes, light moves a fixed distance, 1 light second, 1 light year, depending on the scale. The sides of this cone are always drawn at a 45-degree angle, representing the constant speed of light, the ultimate limit of motion in our universe. No matter what we do, we can never escape this cone. It defines everything that can happen to us and everything we can affect. In Einstein's theory of relativity, these light cones are essential. They define the structure of space-time and determine what causes what, the relationships between cause and effect. Let's understand this with a cosmic example. Imagine a massive explosion happening far away from Earth, a supernova, the violent death of a star. When that explosion occurs, its light spreads outward like our candle, a growing bubble expanding through space. But Earth won't experience or even know about that explosion until the edge of that light bubble, the supernova's light cone, reaches us. When it finally does, we see it as if it's happening right now. But in truth, it may have occurred 10,000 or even 30,000 years ago. Until that light reaches us, the explosion doesn't exist for us. It's invisible, undetectable, outside our light cone. This is causality, the rule that one event can only influence another at or below the speed of light. Now, let's return to the bigger picture. Space and time, what's the real difference between them? In space, you can move in any direction: forward, backward, left, right, up or down. But through time, you can only move forward. You're constantly being carried from the past toward the future, never in reverse. Even if we appear to go back in memories or videos, physically, we're always moving forward, deeper into the next moment. And this is what light cones beautifully show us. While we have freedom of direction in space, time has only one direction: forward. Now, imagine the universe again, calm, empty space with no gravity. Here, space-time forms a flat grid, smooth and regular, where all light cones are parallel. Time flows evenly everywhere, like a single rhythm. But the moment you add a massive object, such as Earth, everything changes. Just as gravity pulls an apple downward, it also bends light. If that apple emitted flashes of light, even those light rays would curve downward, pulled by gravity toward the planet. In this case, the light cones themselves are no longer parallel. They start to tilt inward, bending more and more near the massive object. This means time itself begins to curve toward the planet's center. The heavier the object, the stronger the curvature of space-time. Now, imagine a body so incredibly massive and compact that its gravity bends space-time completely inward, a black hole. Here, even light cannot escape. If you lit a candle near it, every ray of light, no matter which way it traveled, would bend back toward the center. This is the event horizon, the boundary beyond which nothing, even light, can escape. A black hole is like a deep pit in space-time. From the outside, it looks like a perfect dark sphere. Beyond its horizon, time and space twist so severely that the future of everything inside points only one way, downward, toward the center. To understand what happens there, physicists consider two perspectives. One, a distant observer watching from far away. Two, an astronaut plunging into the black hole. To the distant observer, everything looks calm. The black hole appears still, and time flows smoothly from past to future. They would see the astronaut slowing down, moving slower and slower, never quite reaching the horizon, frozen in time. But for the astronaut, things are very different. As they fall closer, space and time stretch and curve violently. At the event horizon, time and space tilt 45 degrees, just like the surface of a light cone. From the astronaut's point of view, the horizon is not a line between past and future. It's a tilted boundary that leads directly downward in time. Once the astronaut crosses it, there's no turning back. Inside, space itself points toward the center, and the future leads only one way, to the singularity. The event horizon is no longer a place in space. It becomes a moment in time, a now that cannot be revisited. The singularity at the center isn't just a point, it's an inevitable future, the destiny of everything inside. When a massive star collapses after a supernova, it emits one final flash of light, a last expanding bubble struggling to escape. But in the warped space-time near the collapsing core, that bubble freezes in place. From the outside, it appears motionless, its light trapped forever. And that's how a black hole is born, a region where the light cone, the symbol of movement and possibility, becomes still, where the past, present, and future all collapse into one direction, downward into the heart of darkness. The universe, through its geometry of space and time, teaches us that nothing moves faster than light, and even light itself can be trapped when gravity bends reality too far. That's the mystery and beauty of relativity and black holes, where light, time, and space all dance in a single cosmic rhythm, the rhythm that defines the very structure of our universe.